We've already been introduced to the concept of the mole as a counting unit. In this video, we extend this idea to a new concept, molar mass, which provides the key to determining a relationship between the amount of matter and its mass, and leads to the most important relationship in chemistry, the molar mass equation. We noted in a previous video that the mole, which is a counting unit similar in concept to a pair or a dozen, has a rather peculiar definition. The mole is the SI unit for quantifying the amount of matter, and it is defined as the amount of matter that contains as many objects as the number of atoms in exactly 12 grams of carbon-12. And that number of atoms is approximately 6.022 times 10 to the 23 when written to four significant figures. This number is such a special number in chemistry, it's given its own name, Avogadro's number, and has the symbol Na. The definition of the mole, whilst peculiar, is clever because what it does is relate the amount of a sample of matter, for example, how many atoms, molecules or ions are in a sample, to the mass of that sample of matter in grams. The reason this is important is because chemistry and chemical equations involve counting amounts. For example, this chemical equation here is a representation of a chemical reaction which can be quantitatively described as one molecule of methane reacting with two molecules of oxygen to produce one molecule of carbon dioxide and two molecules of water. But in reality, we are never going to start with just one or two molecules. We're going to start with much, much more. For argument's sake, however, let's say we start with 12 molecules of methane. Still an unrealistically small number. But if we had 12 methane molecules, we are going to require 24 oxygen molecules to react with them, and that will produce 12 molecules of carbon dioxide and 24 molecules of water. But again, it's unlikely that we're going to be starting with just 12 molecules. What we're more likely to start with is the number of molecules of the order of a mole. So if we were to start with 1 mole of methane molecules, we would require 2 moles of oxygen molecules, and we would produce 1 mole of carbon dioxide molecules and 2 moles of water molecules. And this mole interpretation of chemical equations and their stoichiometric coefficients becomes very important if we want to do something useful in chemistry, like calculating the mass of products produced from a given set of reactants. The problem is, in the lab, we don't count molecules and we don't measure moles. What we typically measure is mass, and we typically measure mass in grams, or sometimes milligrams, or even as high as kilograms. And so to do anything useful in chemistry, we're actually going to need a relationship between the amount of matter, represented in chemical equations and chemical formulas, and the mass of matter, which is what we physically measure in labs. And that relationship is provided by the physical property of molar mass. The molar mass of a substance is defined as the mass in grams of 1 mole of a substance, and it has the units of grams per mole. Now importantly, the molar mass of carbon-12 atoms is 12 grams per mole, and this comes directly from the definition of a mole, where we note that 1 mole is equivalent to the number of atoms in exactly 12 grams of carbon-12. So that definition provides this relationship here, where we have 1 mole of carbon-12 on the left-hand side, an expression of amount, being equivalent to 12 grams of carbon-12 on the right-hand side, an expression of mass. And so we start to see what we said we needed a bit earlier, a relationship between the amount of matter, as represented in chemical equations and chemical formulas, and the mass of matter, which we can readily measure in the lab. At this stage, however, this relationship is just an equivalency. Now, if we wanted to make this relationship an equality rather than an equivalency, then we could take that 12 grams of carbon-12 and we could divide it by its molar mass, 12 grams per mole. What we've got now is a statement that says that 1 mole of carbon-12 equals 12 grams of carbon-12 divided by 12 grams per mole. We can see that this is now an equality because those two 12s cancel out, the grams cancel out, and that leaves us with 1 over a mole as the unit, which equals a mole. So we end up with 1 mole of carbon-12 on the left-hand side equals 1 mole of carbon-12 on the right-hand side, which is undeniably a true statement. Now, those of you with a little mathematical knowledge will quickly realize that we just deliberately constructed a little circular mathematical process to produce a relationship that shows that moles equals mass divided by molar mass. And whilst this specific example involves carbon-12, this relationship will hold true for every other element in the periodic table, since the atomic masses of all elements are reported relative to the mass of carbon-12, as we have already noted in previous videos. So what we have now is a general relationship that holds true for all substances. Moles equals mass divided by molar mass. And this is actually the most important mathematical relationship in chemistry, and we're going to be using it a lot over the course of our chemistry studies. One thing to remember is to never forget the units. The units for moles being moles, the units for mass being grams, not kilograms, and the units for molar mass being grams per mole. Given what we have just seen, it is important that we also understand the relationship between the molar mass of atoms, being the mass of 1 mole of atoms expressed in grams per mole, and the atomic mass of atoms, being the mass of 1 atom expressed in atomic mass units. We know from previous videos that the atomic mass of carbon-12 is defined as exactly 12 atomic mass units, and we also know that the molar mass of carbon-12 is assigned, via our definition of the mole, a value of exactly 12 grams per mole. So we find that the molar mass and the atomic mass of carbon-12 have the same magnitude, 12, but they have different units. The units for atomic mass being atomic mass units, the units for molar mass being grams per mole. We can look at any element on the periodic table, for example oxygen, and we see that its atomic mass, the number under the atomic symbol, is 15.9994 atomic mass units. But we could also interpret this number to be its molar mass as well, but rather than the units being atomic mass units, the units now become grams per mole. So the molar mass of oxygen atoms is 15.9994 grams per mole. And we can do that for all other elements. For example, number 1, hydrogen. We read its atomic mass to be 1.00794 atomic mass units, and we can simply state that its molar mass is 1.00794 grams per mole. The same magnitude as the atomic mass, but we just changed the units to grams per mole. If we look at sodium, number 11, its atomic mass is 22.9898 atomic mass units. Its molar mass is therefore 22.9898 grams per mole. Now that is very convenient. We just take the atomic mass directly from the periodic table and express it in terms of molar mass by changing its units. And that is the key to why the mole was defined as it was and why atomic mass units were defined as they were. Both were defined in terms of the carbon-12 isotope of carbon. Now this relationship, moles equals mass on molar mass, is, as I said, the most important relationship in chemistry. But there are other rearranged versions of this equation that become important to use. So, for example, if we were to multiply both sides of this equation by molar mass, we can make the mass the subject of this equation. Mass equals moles times molar mass. And then if we divide both sides of this second equation by moles, we would get molar mass as the subject of the mathematical relationship. Molar mass equals mass on moles. And these are the 3 different versions of the same molar mass equation. And we're going to have to get used to using all 3 and to be able to interchange between using one or another. In follow-up videos, we will see how to put these equations into practical chemical use and see how we can easily rearrange these equations as required.